Hi everyone. Cole asked me to go over problem number 17 on homework 12, so I just wanted to kind of go over that with you. I typed it up on the pinned discussion board, but I also want to just talk you through it just in case it's confusing to you still. So in this problem, we're supposed to identify the inflection points and local maxima and minima of the following function. And the function is y equals 9/13 times the quantity x squared minus 25 to the 2/3 power. So they actually give you, which is kind of nice, a graph here on the right. You know, you don't necessarily need it to go through all the work, but it's kind of nice to see that and to know that your work kind of looks right once you get these exact values. So we want to identify the open intervals on which the function is concave up and concave down also. So we need both the first and the second derivatives to do these things, right? So hopefully you're comfortable with that. But let me go back to the pinned discussion board where I've typed this up and kind of go through it. Okay, so this is just me typing the problem statement. So again, go ahead and I did not actually attach it as a web page. I just decided to do a video. I apologize. So maybe I can still attach that. I don't know. I don't think so, but the video is better. So anyways, don't worry about it. Okay, so here's the solution. We want to go over this. So local maxima and minima occur at critical points of a function, right? Hopefully everybody's comfortable with that. The critical point is either where the first derivative is 0 or the first derivative is undefined. And then we also hopefully are getting comfortable with changes in concavity occur at inflection points of a function. Where a change of concavity occurs, that is called an inflection point. And inflection points occur where either the second derivative is 0 or the second derivative is undefined. Okay, so we have to look at those values. Note two things when you do this. Not all critical points are necessarily locations of local maxima or minima. And two, not all points where the second derivative is 0 or the second derivative is undefined are inflection points. The concavity must actually change at those locations for them to be inflection points. So we need the first and second derivative. So let's go ahead and do those. So the first derivative, I have to use a chain rule, right? I'm just leaving the constant 9/13 out in front. So remember, it was 9/13 times x squared minus 25 to the 2/3 power. So we got to use a chain rule, bring the 2/3 power down, x squared minus 25, the inside leave alone. The power then becomes minus 1/3. That's 2/3 minus 1, which is minus 1/3. Minus 1/3. Then I multiply it times the derivative of the inside. The derivative of x squared minus 25 is 2x. So simplifying slightly, we have 12/13ths, right? I have this 3 cancels with this 9 to give me 3. 3 times 2 is 6, times another 2 over here is 12. So 12/13ths, I'm left with this x in the numerator, and then I'm putting the x squared minus 25 to the positive 1/3 now in the denominator. Okay, so the reason I did that is so I can go ahead and use the quotient rule to find the second derivative. It's just a little bit easier. I'm going to leave the constant 12/13ths out in front. Then we have low d high minus high d low. So the low is x squared minus 25 to the 1/3 power. D high, the derivative of the top, derivative of x is 1, minus high, x, times the derivative of the bottom. So the derivative of the bottom is the same as what we did before, 1/3 times x squared minus 25 to the minus 2/3 times 2x, right? The chain rule. Bring the 1/3 down, x squared minus 25 to the 1/3 minus 1 is minus 2/3, times the derivative of the inside is 2x. So we have low d high minus high d low. All over low squared, so when I square something to the 1/3 power, it becomes to the 2/3 power. So simplifying this a little bit, notice that each one of these terms in the numerator here have x squared minus 25 to the minus 2/3 technically in them, so I can factor out an x squared minus 25 to the minus 2/3, putting that right here. That means I'm left with x squared minus 25 to the power 1 right here, because x squared minus 25 to the power 1 times x squared minus 25 to the power minus 2/3 would be x squared minus 25 to the 1/3, right? That's how I get that. And then my x squared minus 25 to the minus 2/3 was already factored out of this side, so I'm left with 2/3 x squared, negative sign in front, negative 2/3 x squared. And the denominator is x squared minus 25 to the 2/3 power. So then I have 12/13ths. Now this x squared minus 25 to the minus 2/3, I'm putting in the denominator as positive 2/3. Multiply it times another x squared minus 25 to the 2/3, it becomes x squared minus 25 to the 4/3. Okay, and then the numerator is now x squared minus 2/3 x squared is 1/3 x squared minus 25. Okay, so y prime equals 0 for x equals 0, right? To figure out when a rational function like this is 0, you set the numerator equal to 0, so x is 0. It's undefined when the denominator is 0, or when x squared minus 25 equals 0, which means that x equals plus or minus 5. So those are my critical points, x equals 0 and x equals plus or minus 5. Right here I wrote that. Critical points of the function are x equals minus 5, 0, and 5. The second derivative is 0 for when its numerator is 0. 1/3 x squared minus 25 is equal to 0, which means that x squared is 75, which means that x is plus or minus the square root of 75. 75 is 25 times 3, so the square root of 25 is 5. Left with the square root of 3, so plus or minus 5 square root of 3. Y double prime is undefined when its denominator is set equals 0, so it's also undefined for x equals plus or minus 5. So those are all the possible inflection points, plus or minus 5 square root of 3 and plus or minus 5, listed in order from left to right here. Okay, so since the first part of the problem asks for the inflection points, let's look at the sign of the second derivative to find the concavity of the function, right? The second derivative is how we determine whether a function is concave up or down. If the second derivative is positive, it's concave up. The second derivative is negative, it's concave down. And we're going to look to the left and right of each possible inflection point to see if the concavity actually changes, then it is an inflection point. So to the left of minus 5 square root of 3, square root of 3 is about 1.7, so 5 times 1.7 is less than 10. So we'll look at x equals minus 10. That's to the left of minus 5 square root of 3. Plugging that into the second derivative, we get 1/3 times 100, so about 33 minus 25. That's positive, and then this is also positive, right? This denominator will always be positive for the second derivative because I'm taking something to the 4/3 power. Take something to the 4 power here in the numerator, that's always positive. Okay, so denominator is always positive. So I just have to look at the numerator here, and I see that that's around 33 1/3 minus 25, so that's positive. So that means the function is concave up on minus infinity to minus 5 square root of 3. So now just to the, in between minus 5 square root of 3 and minus 5 actually. So I'm going to look at minus 6. It's a decent number in between there. Look at second derivative at minus 6. Plug that in. This is 1/3 of 36, which is what? That's about 12. So 12 minus 25 is certainly negative. The denominator is always positive, so that's negative. So we do have a change in concavity because from minus infinity to minus 5 square root of 3 it's concave up, and then from minus 5 square root of 3 to minus 5 it's concave down. So that means that minus 5 square root of 3 is actually an inflection point. Okay, I'm going to check between minus 5 and 5, so I'm going to choose x equals 0. I chose that one because it's easy, and 2 because I also know that's a critical point, so it's also going to tell me something about whether that critical point is a maximum or minimum. We'll talk about that in a second. So second derivative at 0, plug in 0, that's certainly negative. Minus 25 is negative, the denominator is always positive. Minus 25 to the 4/3 power is positive. So that's a negative number, it means I'm concave down. So it does not change concavity, but we wouldn't expect it to because we just need to look between, no, that's right. We're checking between minus 5 and 5, sorry. So I checked 0. So it does not change concavity at minus 5. So minus 5 is not an inflection point. Now I'm going to look just to the right of x equals 5, but not all.